and we're going to hear. Perfect. I'm going to hand it over to you now, Greg. Everyone who has questions, please feel free to type those questions up in either the Q&A or the chat box as we're going tonight. We're going to answer those questions at the end. There will be a time for that. And this video is going to end up on YouTube, and you'll get an email from me tomorrow with the link to this recording. So thank you, Greg, for speaking to us tonight, and I'm going to give it over to you.
Okay, well, thanks for inviting me. This has been great. I was born and raised outside of Philadelphia, so I sort of started as an East Coaster, but my first and went to grad school then at University of Kansas, University of Wyoming, and my first faculty job was at University of Buffalo, and then I was down at University of Tennessee in Knoxville for a decade, and then did a little more at University of Kansas, and now I pushed my way out here to the Western Slope. So clearly, as I get older, I'm gravitating, I think, towards where I want to be and love to be. So, but the main reason I bring that up is I got hired in fall 2019. So sort of COVID is my normal out here, and so one of the reasons I especially appreciate this opportunity is because, you know, the Canyons Association, this kind of thing is things that I would have sort of tried to scope out and see who's doing what in new area that I moved had we not, you know, had our lull in COVID. So I do appreciate the invite, and I look forward to sort of staying in touch with y'all and seeing what you do through the time. So, you know, I as a student of history, among other things, I like getting a handle on where I sit in the realm. And of course, George Bernard Shaw famously said, "Those who can do, and those who can't teach." And rather than sort of being slighted by that, I sort of just updated and said, "Those who can understand, teach." And I'm sure those of you who are educators in all different ways, shapes, and forms can appreciate that I always felt that the best teachers were the ones who actually understand a subject the best, because, as you well know, getting all sorts of questions from left field from students, or trying to explain things to people that are either particularly complicated or non-intuitive or something like that is the way to go. So what I'm going to talk about is what the heck is geophysics and why would I care? I've been a geophysicist essentially my entire academic career, and so I'll sort of talk about that. Throw in sort of the first part, I'll be talking about geophysics in general. Some of you may be certainly familiar with components of things that maybe you don't really think of as being geophysics, but they're clearly there. And then I'll sort of finish up with a lot of the things that I've done personally. So it'll sort of be a combination of overview and then things I've done personally. And it'll be pretty clear, I think, by the time we go through this, the way in which geophysics could be of particular interest to you know, tackling public lands problems for sure. So as a reminder, I do what I do because I love teaching, and mainly what I love teaching is watching all of the all the light bulbs go off in the heads of these students when you know, take them and talk to them about what they're looking at in Uniweave Canyon or up in Dominguez, or you know, we were just today driving up Little Park Road. I took a van full of students up there talking about sedimentary rocks and depositional environments and all that. So it's certainly something that I love to do, and it's a perfect laboratory for doing these things. So I'm what I consider an applied quantitative field geoscientist. So you know, geology as a field, I always like to remind people, you know, my professors that I had as an undergrad, they were never taught plate tectonics. They sort of, a lot of my professors predated that being sort of something that came along in the mid 80s and was really the big revelation in the field of geosciences, not only because it put together a lot of things that were either disparate in the world in which geologists understood what they were looking at, but it really pushed forward making geology quantitative. So prior to really understanding how the world works, a lot of geology was qualitative. It was descriptive. It wasn't necessarily putting numbers on things. It was describing things. You're describing a glacial moraine. You're describing cirques and arêtes of glacial terrain, right? You're describing differential of erosion between sandstones and shales. And really where we became sort of modernized as a field of science, this has really only been since sort of the mid-'80s in my perspective, which means, as a science, it's relatively new. What I always tell my students is great about it being relatively new is there are lots of questions that are still out there to be answered. So I sort of study how the Earth was. I do a lot of studying how the Earth is. And then, of course, the reality is science and the scientific method is about generating hypotheses that are testable. And those hypotheses that we put together are really all about making predictions, right? I tell most people, although science is great for figuring out what happened in the past, the real sort of benefit to humanity is how we predict things that may be happening in the future. So I also study how the Earth may be. And I'm a big fan of the scientific method and hypothesis testing. And of course, when we quantify data, when we put numbers on things, that knowing the field of statistics, that makes a lot of hypothesis testing better. But I was born and raised loving the outside. So, what I am not is I'm not really a lab rat. Thank goodness we have people who love those things, because a lot of times I may send them my data and they do beautiful and awesome things with them. But I'm a big fan of being outside collecting data. But what I do is I like being outside and then using really expensive toys. And my data are generally all very quantitative. I've been pretty lucky to have run projects with students a lot of places around the globe. But when I show this map, I always am reminded myself, and I'm often reminded of people how many holes I still have. So there's a lot to be had out there, and I'm pretty excited about. Even at this stage of my career, thinking about problems that can be tackled globally. So, if you were to take a look at papers that I have published, sort of in the last decade, a little decade plus, it's a little bit over the map. On one hand, I'm very interested in the science of education. I'm very interested in working within a framework of classroom transformation and thinking about the impacts, but I want to quantify those impacts, right? A lot of teachers are well known, and I will be one that would be included to sit back and say, well, in my class, I do this, but what's really nice is to have some actual data to know whether that actually makes a difference or whether you just think it makes a difference. So I've done work in sort of lots of different ways of doing education with the geologic side of things. In some cases, that may be helping on the education front to work with other scientists. So one thing that can happen is that geophysics can sort of be either a bit abstract or not very intuitive in the way in which it would convey information about the Earth. So it's useful to do things and use simple and modern tools like Google Earth to help people like archaeologists better represent what's in the data. But I also do a lot of work. I love glaciers. I have done a lot of work up in Alaska over the years. But in between that and tying with that, most of the problems I work on are what we would consider, geologists would consider near surface. So I'm going to say upper 300 to 600 feet. So either landscape or shallow subsurface. So not surprisingly, that would be one of the reasons I'm interested in glaciers, because of their impact on the surface, and they're relatively shallow themselves. But then I also spend a lot of time working on environmental problems, and in particular, looking for clean water, looking for contaminated or dirty water, thinking about remediation problems, those kinds of things. So I do a lot of geophysical methods. You can see things in here related to nonlinear deformation and seismic reflection and ground penetrating radar and things like that. And so those are my tools. So the tools that I use as a geophysicist, there are a lot of them. So a lot of people will use a lot of magnetics, electrical resistivity, heat flow. People now, if you've been paying attention, there's some new really cool imaging techniques that are used with muon collectors and looking at cosmic radiation. That's how they just recently found a new chamber in one of the Great Pyramids. So I like that. I like the idea of using sort of, I'm a nerdy guy. I love using sort of sophisticated equipment and working with that equipment on interesting problems. So one of the things that we did relatively recently, 2017, because not that recently anymore, for those of you who know James Balog, he put out a documentary called Chasing Ice, and he was actually one of my co-authors, and we put this article out on savoring the cryosphere, where he put in all of his sort of imagery that he's worked on over the years, and then my colleagues and I put in the science on the backside of that. So between that and doing interesting things like going back to original field books of Charles Darwin and digging out some of the descriptions he had down in Tierra del Fuego and reanalyzing some of those data. But then again, doing things like understanding frequencies of unconsolidated earth materials, working with archaeologists. In this case, we were doing some work in central and southern Jordan. And then also, like I said, doing environmental work. In this case, I work with several colleagues at Oak Ridge National Lab. And to wrap that and package that all back together, again, one of the things I'm a big fan of is recognizing this idea that diversity of ideas is really a linchpin for good science. And so diversity of all its forms is critical, and it's one of the things that I think we're beginning to do a better job of, certainly in the geosciences. By the way, here are some of Darwin's boulders, and what's awesome is in his field books, he's actually got a sketch of this thing, and so you can actually go back and stand on the same boulder that Darwin stood on, which is particularly cool. So with that big, long sort of overview, when we talk about geophysics is using quantitative methods to get physical properties and understand the Earth. So we're utilizing things other than our eyeballs, things other than our nose. I teach intro geology, and even though with COVID and everything else, we don't do it anymore, right? We can even use our taste, right? We can identify if it's halite versus gypsum or some other mineral using that kind of stuff. So instead, what we're trying to do is solve problems that are either impractical or impossible or maybe prohibitively expensive to do any other way. And the example that I would give is, if we have a groundwater contaminated site, really the best thing you could do is dig the whole dang thing up. But in a lot of cases, that's both prohibitively expensive, maybe impractical, or maybe in some instances impossible. So are there ways in which you can approach what you ideally would want to do, for instance, removing all the contamination from a certain groundwater plume, and get as close to that as possible? And it turns out geophysics is one of the ways of doing that. And of course, the analogy I always use, anytime I run into anybody who's maybe a little skeptic and say, you just show sort of rainbow colored fancy pictures and they mean something, I just remind them that really almost everybody trusts the medical people who are using imaging in medicine, right? We see an image like this and we don't question it. We don't think this is made up. I mean, maybe there are fringe conspiracy theorists who do, but this is an actual image generated, in fact, using geophysics in this case. Rather than looking into Mother Earth, you're looking into a mother. So it's the same kind of thing. In this case, you're bouncing seismic waves around there. Ultrasound, you're using vibrational energy in the same way that we do in the subsurface. So just to summarize some of the things that we do with geophysics, I'll talk just very briefly about work of others looking at Earth structure and evolution of Earth on a global scale. You know, we live in this incredibly sort of vibrant, what I call geology community of rocks out here. And there's a lot to look at. We can, of course, also, the downside is, right, some of these things are particularly devastating. Okay, we certainly, our hearts go out to the folks in Turkey and Syria, and these things are going on all the time. But we'll talk a little bit about fault zones and earthquake cycles, thinking about how we can potentially help preserve more human life in these activities. I'll talk a little bit about global ice volume loss here, and then a little bit about sea level change, volcanic activity and prediction, space exploration, right? These things are all geophysics, right? I do remind people that we've yet to set foot on Mars. So in fact, everything we know about Mars is geophysics, right? It's not using our own senses, it's sending things out there to do things. So, right, so the first thing we can think about is that we know what we know about the inside of the Earth exactly the same way that we know what we know about the inside of an expecting mother. In this case, rather than a little ultrasound wand, we have earthquakes that send energy signals through the Earth. And as these energy signals interact with what's inside, we build models of what's inside. So, right, we've never been there. I always remind my students, even if you took a diagram like this and it was true to scale. In fact, these little mountains on the top here are way too large. You can't even see them on the Earth relative to scale, but you would have to take a fraction of a pin to scratch as deep as humans have actually drilled into the subsurface of the Earth. I mean, if Earth were an eggshell, we haven't even penetrated the eggshell 30% yet. So most of what we know from the inside of the Earth, just like the inside of a mother, we get from our remote sensing techniques, right? Our geophysics techniques for understanding what's going on. And we've gotten quite sophisticated now. So in fact, without going into the gory details here, we're actually able to build much better and much higher resolution images. These are slices of the mantle and crust of the Earth at different components around the world. Here you can see it's sitting out here in sort of the East Central Pacific. Here we're in the Central Pacific, South Central Pacific, and then sort of West Central Pacific. And in particular, what we were looking at, I say we, I'm sorry, this is not my research. What geophysicists are looking at is trying to recognize hotspot volcanism as it may correlate to island chains like Samoa or Tahiti or Pitcairn, McDonald. We know what's going on pretty well out in Hawaii, but there are a lot of these other things that are going on deep in the Earth that we're only beginning to understand because we have more and better data. So in the same way that I tell my students all the time, I say, scientists owe a great debt to cell phones as much as we rue their existence when students are maybe in the back of classroom or something doing this, because all of the speed and compact nature and low energy cameras and Wi-Fi and everything else has made a tremendous amount of things possible. So these kinds of images, which are much more than sort of I looked at in my early days of my early textbooks, these slices are now in this part, which was generally drawn homogeneous when I was a student. We now know that thing is anything but homogeneous, and now we're trying to figure out why. And in fact, some of you may have been involved in the US array experiment. What was done during that experiment was that each of these triangles here represents a seismometer, and those seismometers were deployed across the US in sort of little squares over little square areas. So it was a a mobile system of seismometers monitoring ground vibrations from earthquakes, and ended up with about 2,800 different positions collecting earthquakes from different zones. And one of the things that came out of that is we have a much, much better image now of what's going on directly beneath the crust. So again, going back to this diagram, we now, if this is North America here, have a much better idea of what's going on just right underneath the crust. And then we can begin to tie that into what may be going on in the mantle and thinking about complexities in the way in which we work. And even those are getting more detailed as we deploy more and more sensors in the subsurface. These are earthquake seismometers, but what you can see is this profile is actually made of about 250 earthquake seismometers recording a single earthquake event. And those are used through time to build, again, much more detailed models. So notice here, this depth, rather than being hundreds of kilometers, which is what we see when we go down into the mantle, this is sort of the top 10 kilometers or 20 kilometers. Think about that. We drive that far. The deepest borehole that we've ever done is 29 kilometers, by the way. It's a Russian borehole. It's called the Kola borehole. And every once in a while, some new technology comes along. Somebody tries drilling it a little bit deeper. They drill until they destroy the drill bit and melt everything out at the base. And then they wait and try it again a little later. But that's as deep as we've gone. And that's just one hole, because that thing has, cost millions of dollars. And so once again, when we get back to that idea of prohibitively expensive or impossible, right? We'd love to grab some sci-fi spaceship and get down here and look at the MOHO, or even the Mohorovic discontinuity, which is the base of the crust, or get into some other interesting area down there. And we're now building sort of interesting three-dimensional models. So in fact, for those of you who may have taken introductory geology out here in the North Pacific Northwest of the United States, we have Washington, Oregon, Idaho, California, and Nevada, right? We're sitting in over here on the other side of Utah. This Juan de Fuca plate is actually being subducted beneath the North American plate, and associated with that subduction is a large amount of volcanism, right? Mount St. Helens famously, but Mount Rainier, Mount Hood, my favorite, Mount Baker. And we've actually done the job now of imaging that Juan de Fuca plate as it's going underneath the North American plate. And one of the things that we're seeing is where it has sort of gaps and missing components, maybe that's coming into play what was going on that made the Snake River Plain from the hot spot that is now sitting underneath Yellowstone, and some of the other volcanism that we see going on. So again, this is all geophysics. One of the things we're able to do with geophysics in 2015, there was a 7.9 Nepalese earthquake. And with geophysics, we can now do things because we're collecting data with satellites now. We can measure pretty small, subtle motions going on during earthquake events. And so in this case, we can look at places that were depressed below the subsurface and places that were lifted up during major faulting events. And we can also then translate that here, this hotspot map are areas that are prone to damage because of where either the type of rock they're sitting on, usually it means they're not sitting on rock, they're sitting on loose soil or steep hill slopes or things like that. So we can make hazard hotspot maps. And if we then use the geophysics data that we acquired from the earthquake, we can say, okay, here's another region. If we had that same motion, where would we expect to see the particular damage, and can we improve things for those people? So, the other things we can do if we're trying to think about sea level rise and the effects of global climate change is we're really interested in what's going on with the Antarctic ice sheet. And so we, in fact, do the same thing on Antarctica. We can collect seismic data from vibrations, but we can also now collect GPS data to look at motions and velocities. So we can link motions and velocities of surface ice to ice quakes. And in fact, that's what this thing is. This is instead of an earthquake, this is an ice quake happening as this convergence of flow, fast convergence of flow because of the warming ice sheet, is creating a lot of these fractures, which then when they get out into the ocean are allowing for seawater to come in and melt the ice faster than we had previously expected, right? We can use those data to look at some of the implications of melting ice. So one of the things we can look at here is things that we may see in terms of global rebound as ice sheets thin. So in other words, as the the Greenland ice sheet or the Antarctic ice sheet, as those ice sheets thin, one of the things we see happening is because we're unloading that part of the crust, those parts of the continents will actually be lifted. And so, in fact, when you look here, these red colors are showing areas that are actually undergoing an increase in elevation because of the melting ice mass. So interestingly, in some cases where we're going to have both a significant species devastation and a great deal of warming, in fact, one of the things most of the Arctic and Antarctic will not have to contend with is rising sea level, because those parts of the crust are actually going to be lifting while all of the ice is melting. So our understanding of where all these human hazards will happen are fully based on geophysics, and these kind of models are getting better and better realized because we have a much more firm understanding of what's underneath the surface of the earth, right? So again, I won't go too more in detail, but we can think about hazard maps. In this case, these particular hazard maps say if we had a big magnitude 9 earthquake near the Mendocino Triple Junction in Northern California, this would be how many minutes of warning you have along the coast, okay, associated with big surface wave ruptures, and then subsequently, if there were going to be any tsunami associated with those. And you can see that that works both ways. Again, Northern California into San Francisco area, or Southern California into the Los Angeles area. And so if we start thinking, knowing the data and the travel time with these earthquake energies, we can build better hazard maps, okay? All right, I'm gonna skip through a couple of these, and I hate to because they are tantalizingly good, but I kind of want to get to my own cool stuff. But here we're looking at an image of Hawaii. We're thinking about some of the recent eruptive flows that took place in Hawaii. And just so you know, this map in here is actually only about a 5-year period of earthquakes. So one of the takeaways I always like make sure to have my students have when I'm talking about earthquakes is they're happening everywhere, all the time, all around the world, right? So as I sit here, there are magnitude 4 and 5 earthquakes happening. Just fortunately for us humans, the planet's 2/3 water, so most of them don't affect us unless they generate tsunamis. And even then, there's huge amounts of the planet in Antarctica, Greenland, middle parts of Australia where these earthquakes happen and nobody notices. So where have I found geophysics particularly useful? And by the way, I apologize for looking down at my watch. I'm just setting myself a timer so I don't go over time here. So I want to go through a couple of case studies. So again, if you've caught it already, I'm very interested in glaciers and glacial processes. I'm very interested in groundwater contamination. And one of the things that I've begun to tackle since 2019 when I moved out here is looking a lot more at landslides or mass wasting and wildfire-related slope erosion, right? Where we get degradation of slopes causing an increase in downward motion of sediment, which used to be locked by all the vegetation that burned up. That sediment gets into the rivers and streams, which then transits down gravitationally downhill, ends up depositing that sediment in reservoirs, wreaking havoc in those kinds of systems. Also having a significant change in sometimes positive, sometimes negative in various ecosystems and that kind of thing. So let me go ahead and just throw a couple of things out there. So in terms of glaciers and glacier processes, as I mentioned, not only do I love the surface, but I'm an ice guy. So I was pretty excited to get to know James Baylog pretty well, and he spent a number of times documenting things. But as a reminder to what I mentioned in the beginning, he was certainly doing this for a different reason, right? But this is pretty qualitative data. Now you can get in here and try and do some measurements on different things, but the main thing is just to make people gasp, to just have an impact, right? So these are about 30-year apart photos. You can see this sort of intruding granitic rock here is the same thing as that. This peak up here is the same as that peak here. And you can see in a 30-year period, we've taken this mountain glacier, this particular one is in Alaska, and that's gone all the way up the just to the mouth of the fjord here. In fact, we see a similar situation down here. This is the Matanuska Glacier in Alaska, where I'm going to show you I did a little bit of work. And in fact, if you look, this is where Matanuska used to be, and now the terminus is working way up here. And not only does this have all the impacts and implications that you probably know about in terms of the main ones I think of is not only are these contributors of water, but marginal contributors of water compared to what we see in Greenland or Antarctica or the Himalayas, what a lot of people call the third pole in terms of ice. But one thing that's becoming pretty evident is with the mass retreat of a lot of these glaciers, when they start leaving exposed fjord banks on either side, these things are then pretty ready to go in terms of generating mega landslides in places where there may or may not be humans downriver from these events. You might have seen there are a few movies out there about this very thing, because as the glaciers scour these valleys, they make near vertical shear walls, right? Just think about Yosemite, but this is happening incredibly rapidly. And so those walls have no time to sort of naturally relax through a slow retreat of a glacier. They're just sort of exposed at the surface. So just another set of photos, right? You can see a lot of these glaciers that are working their way or were working their way down out of the valleys. They're now pretty far up in the valleys. And in fact, the other thing that's interesting is these two photos here were taken at the same time of year. And in fact, you can in fact see the greening there that one sees in the Arctic now, where we're getting not only increased warming, quite rapid warming compared to the equator and the temperate parts of the world, but we're also getting these places greening up much sooner. Again, another before and after shot. You can see this thing is almost completely gone. And so one of the things that my authors and I talked about in sort of this global view, this is a figure I unfortunately won't have a lot of time to talk about the details, but ultimately I want you to look at the big points here. So the first thing I want you to notice is here's India, here's China, this is the Himalayas along here. And this is that thing that a lot of people consider the third pole. It's the third largest volumetric region of ice on Earth. It's a fraction of Greenland and especially Antarctica. But what I want you to see is that this is the source for all of these river systems, right? All of these river systems here, from way out in the Middle East to India to working our way down and eventually out into the Indian Ocean and over here in China. Every dot on this map is a city of at least 1 million people, okay? And of course, that's at least 1 million people. Some of these cities are tens of millions and even larger than that. But the point is, all of these people, okay, are watered from the water that's sitting in the Himalayas. And we're seeing pretty substantial ice change rates throughout the Himalayas. And although right now that's good because that's putting a whole bunch of water down in here, sometimes it's bad because it generates flooding. And of course, ultimately what's going to happen is there are going to be no more deserts. It's just going to be a high, dry environment. Now, no more glaciers. It'll just be desert, a high, dry environment. And all of these folks who live inland away from the ocean are going to have to figure out ways to get water. And of course, as we know, water is critical for human habitation. So here's some of the work I wanted to show you, just to show you where this idea of quantification comes into play. One of the things that people are very interested in is when we take a glacier like the Matanuska Glacier, which flows out of the Chugach Mountains in Alaska. It actually flows to the north. All of the glaciers you may be more familiar with down in Glacier Bay and sort of the Princeton, Harvard glaciers and all those are all glaciers flowing out into the ocean. This is the Chugach Range on the coast. These things are flowing north. But what we're particularly interested in is the way in which glaciers transmit sediment. Now, you may say, what's the importance of that? Well, one of the reasons that when one looks at a map of the United States and looks where a lot of the sort of so-called breadbasket regions are, yes, some of theirs are in the river valleys, but the majority of our high growth regions are in areas where the United States has been formerly glaciated. And the reason that's important is because you pull all the rock and minerals from a very disseparate region, and you start dumping and pumping that down and generating this very nutrient-rich, very rejuvenative sediment. And one of the issues that people are wondering now is, what's that linkage between sediment and glaciers and the rate at which they melt? So one of the things I did is I did a sonogram on a glacier. These things out here are my seismometers or my geophones. What we did out here, I think, I'm going to show these data next. What we did out here is we'd go out here and we'd hit the ground with a sledgehammer, or we'd impact the ground with a weighted drop and send that sonic energy into the ground. And it would go down and transmit through the ice and ultimately get to the very bottom of the ice. And it turns out the very bottom of the ice is this sediment-rich region that we're particularly interested in. So what I want to show you is we collected a couple of profiles. This region of the glacier was heavily crevassed, so we couldn't collect data there. But this first dominant reflector here is actually not the bottom of the glacier. It's the bottom of clean ice. And it turns out the bottom of the glacier is packed full of dirty ice created when supercool high pressure water releases its pressure when glaciers flow up out of over deepenings, and those ice crystals lock that sediment in the base of the ice, which then when it goes out and melts, now you've got all your debris. So even though we get a lot of superglacial landslide material, a lot of the fine grain nutrient rich material is actually coming out of the base of the ice. And we know more about that now because we could get these quantitative data and begin to measure out what is the thickness of that basal ice. This is how we ground truthed it. This is a well that was drilled about 100 meters down, about a football field down into the ice. These things are kind of fun to watch. You'll forgive if this offends, but essentially it's this brass tube, and you furnace very hot water, and it's kind of like pissing your way into the snow. So this thing just puts out a high pressure stream of hot water, and it melts its way down through the ice. And what's cool about this when we're interested in sediment is as it melts its way through the ice, when it hits sediment-rich zones, it begins to jump and bump around because there's sediment there and not ice. So we actually caught an earlier debris band down in here, and then we get the top of ice, and then finally we get to the bottom where we can't get this thing to go through dirt. It won't go through dirt. And when we measure those out with our data, here's where our hot water drill saw the top and the bottom of that basal ice. What you can see is we're within about a meter from what we estimated from our geophysical data, with the exception of this one, but this thing is what had one of those debris bands coming through. So it's probably an error in us estimating where we thought the top was. So where did that all come out? Well, we published, this is a figure that was in one of our papers that came out in Nature magazine. And particularly what we're interested in is what happens with glaciers as they thin. And that, of course, is happening as they melt out. And what thinning glaciers tend to do is build these larger sediment buttresses in front of themselves as compared to those thicker glacier systems. And in fact, we could track that then on the Matanuska. We could test this hypothesis. And as a result, this suggests that we're definitely going to be getting, because of this supercooling system related to the thickness and gravitational potential of ice, as these things are getting thinner, what they're beginning to do is translate that into a much larger sediment load, which then gets into all the river systems that are going to come out of any place where we have glacial ice. Well, let's switch gears, talk a little bit about groundwater and groundwater contamination. So, there's a lot to think about when we think about that. So most people have some intuitive understanding of, what is a water table? So we get rainfall, it percolates its way through the soil or cracked rock, and at some point it fills up 100% of that space with water. And then we're left with this region that has just soil moisture above that, and that's what we get as our water table. Well, turns out that's a pretty simple system. And when we look at the way the world really works, is we not only have those shallow aquifers that are of some use, but what many of you know is there are actually deeper aquifers. When we go out here into the Grand Valley, we mainly have three substantial aquifers, some of which go down quite deep. And those aquifers are essentially when we have sandstones interbedded with shales. Those shales have a lot of clay, which prohibit the water to flow through. But the issue is, as we have these multi-level aquifers and we're doing different things on the land surface, those different things on the land surface will have different impacts and implications for different components of the aquifers. And what, of course, shouldn't be surprising is the deeper the aquifer, the more expensive it is to get that water. And so not only are there social justice implications for this, where these shallow aquifers get polluted easy, the deep aquifers, the expensive aquifers are a little bit harder to produce because they are essentially protected by the overlying aquifers that get polluted until they're unusable. But in fact, even some of these deeper aquifers have things going on with them. And so understanding the geology, understanding by using geophysics what's going on in the subsurface makes us and helps us to understand these things better. And when we think about water in the rock, there are really sort of three types of water in rock. There's water that's in between pore spaces of granular rock, okay? There's water that flows along cracks and joints in fractured rock, okay? And then there's water that flows in caves and tubes of limestone rock, right? Like karst. Well, of these, the hardest ones are the ones with the fractured rock system. And of course, therefore, those are the ones I like to tackle. And why are fractured rock systems particularly bad? Well, here's a simple example. If we have a leaky landfill at the surface and it's putting a groundwater plume into the subsurface, that groundwater contaminant may be finding its way over to a community well through a complicated set of fractured pathways. And when someone goes out to try and remediate this environmentally contaminated site, you could drill a bunch of wells in the ground that are in between the landfill and the contaminant site and never hit any contaminant, completely miss it, because these things, again, can be sort of hard to find as they're sitting their way through the system. So one of the things I like to do with geophysics is work these things out. How can we see these fractures? So here are some numerical simulations to just get you thinking about this. So this top part shows a rock fracture where it's more open and less open. And then this shows a groundwater, which shows how that pathway of that contaminant would be very complicated flowing its way through. So again, if we have just a porous media with contaminant flowing through versus if we have a complicated fracture, you can see you could even go straight down the flow gradient and suddenly you're looking for contaminant. You don't find any of it, even though it's showing up down in the creeks or the river systems or that kind of thing. And it gets even worse if you look in 3 dimensions. Here's a here's a well going from the surface to depth. So we're looking at a cross section now. And what you're actually looking in is one plume coming out of the screen going along and a different plume going in a fracture set in the screen and flowing slightly in a different direction and different elevation. These things are a mess. So we want to start looking for these fractures. And part of the reason we do is there's something called the cubic law. And the cubic law states that the amount of water you can push through a fracture is as the cube of the fracture size. So in other words, if you have a fracture that's 1 millimeter, okay, and then you have a fracture that's 2 millimeters, that 2 millimeter fracture will be able to carry 8 times as much water, okay? And so I've done some experiments. Here we are at some rock. This is some rock at the surface. And what we're interested in is the fact that this rock has vertical fractures. You can see one of them running along here. You can see another vertical fracture running along here. You can see one running along here. This is in the Adirondacks, by the way, in Eastern New York, but I'm working up some similar experiments here in the Grand Valley area, because probably a lot of you have seen that. You probably looked at tops of rock and seen those variations and fractures. Here's what that rock looks like in cross section. So you can see there are horizontal layers in the beds of the rock, and they will get intersected by vertical fractures and cause that fractured flow. So these horizontal lines coming through here, okay, are the beds and the layers of the rock horizontally. And by the way, this is ground penetrating radar. So in this case, rather than looking with seismic sound waves, I'm looking with electromagnetic radar waves. So we have our horizontal fractures. And interestingly, we can see our vertical fractures. You see these herringbone patterns. Every place you get this herringbone pattern is showing you exactly where the boundary of a vertical fracture is. And so one of the things we're able to do with our geophysics tools is we would be able to go out to a contaminant site, locate these fracture networks, and then just do a much better job of remediating these surfaces. And in fact, what this map shows we were able to do is we were able to actually extract the amplitude of the reflected energy off these reflections from these different fractures and make maps of fracture aperture. And remind yourself, if we can make maps of fracture aperture, we can make these kinds of maps, which show us where we would be able to predict that flow. So again, this loops us all the way back to science, and the scientific method is about making predictions and using those things to help us in the future, okay? I want to give enough time for questions, so I'm going to skip this one experiment. You would love it because it involves a Walmart kiddie pool, and it involves an 800-pound block of PVC plastic. So I'll only briefly tell you, all we were doing was synthesizing our own fractures. We wanted to quantify our data, and ultimately what we were able to do is predict that you could tell the aperture of a fracture using these controlled experiments by what the reflection amplitude was on these fractures. So these were our wider fractures, these were our thinner fractures, and we were able to work that stuff out, come up with some mathematical relationships, which would allow us to do this prediction in the future. Here we are at the Oak Ridge National Lab. If you ever want to read something horrible and interesting at the same time, these are called the S3 ponds, and essentially these are super saturated, super contaminated ponds in Oak Ridge National Lab that not only had insane amount of nitrate contaminant, but also uranium contamination in them. And the amazing thing is to go back and read the manager's logbook. And one manager has been quoted to say, and this is pretty close to an accurate quote, "We love the S3 ponds because we can keep putting water and our outage into these ponds and they never overflow." And so, of course, that meant, where did it all go? It was all going underground. And so, in fact, 2.5 million gallons per year from 1951 to 1983 went in here, and a vast majority of that water and contaminants went into the subsurface, instead of what the plan was to let the water evaporate, scrape it out, put it in a moderate radioactive contaminant site. So one of the things I worked on here, and I'll skip to the crux of this, was looking at fractured rock in the rock that's below this uranium contaminant site to help us figure out what's going on. Now, today, those ponds are covered with a parking lot, which any of you who know water know this was a horrible idea, because now anytime it rains, rain hits the parking lot, and the idea was to keep the rain from going into the contaminants and pushing it out. But now you get huge volumes of water rapidly rushing off the edge of this parking lot into these drainage ditches, which in fact makes the problem even worse. So they've gone back now and figured out ways of porting that water way off site. As we know, for humans, things get worse sometimes the more we try and fix them. So here we are with our seismic data, and the long and short of it is we were trying to map out how these fractures, in this case in limestone, were causing karstification, were causing sinkholes and channels, and we were mapping out these channels associated with what we would call low velocity zones in those limestones. And as we map those out using these seismic images, we could track this thing through time, and we could map out those pathways, those primary contaminant pathways, to where they were getting into some of these streams downfield. Okay. I've got another great experiment in here, but I don't have time. I'm not going to show you that one later. Ultimately, here we were just dumping water in the ground to see how well we could image it. And you could see as we dumped that barrel full of water into the ground, we could image that with the geophysics data. Why would we want to be able to do that? Well, one of the things we're really interested in is when rain falls on the ground, how does that water migrate, right? Does water hit the ground and migrate sideways? Does it hit the ground and short circuit straight down? Or does it come into some sort of short circuited flow off at an angle? So for contaminant sites, that pathway of migration is incredibly important, and we've been working on it. So the last thing I can tell you about, two quick ones, is one of the things I've been looking at is stromatolites in Puerto Rico. These are in abandoned salt terns. And if you don't know, salt terns, here are an example, have been used by humans for thousands of years. You build these near the coast. You hand dig a little pathway between the ocean and your little pits. You let the seawater in, you fill that back in, you let this water evaporate, and then you scrape the salt off and you sell it to people. Well, interestingly, as these get abandoned, they're becoming really high, let's call them extremophile sites. And interestingly, what's happening now is we're actually growing stuff in these things that have pHs in the 2 to 3 range during the summer. These are shallow water, and temperatures in here can be well over 150 degrees Fahrenheit. One of the issues associated with the low pH and the super high temperatures is you can't actually get out here with waders and sample the water, because you can only be in for about 30 seconds or a minute before you superheat your feet, even in some good insulated waders. So at this particular site, I've been doing a bunch of drone data. So that's my latest geophysical tool, is to go out and fly areas that it is, once again, challenging or prohibitive to collect data to find out information. So in this case, you can see people are down here sampling. Here's a pair of hot rubber boots that somebody abandoned. And what we're particularly interested in is these stromatolites. These are like early life on Earth growing in these extremophile environments, which tell us not only about early Earth, but potentially things that could be growing on Mars. And so one of the things we can do is we can come in and use that drone imagery to get some idea of what's going on at the surface. Now, I will admit to not having often shown these videos in a Zoom context. So it may be that the resolution of this particular imagery is not great. So for that, I apologize. Looks okay on my screen. So this is a fully digital 3-dimensional surface model created from drone data. And part of the reason, again, for those data is to be able to get quantification. So we're not only looking at sort of gitcha zones or areas where we get some slow winter growth of material, but we're very interested in what is going on in these areas with the stromatolites. So again, we can come in here, look at these stromatolite regions. Here you can see a couple of random footprints of people trying to get through. And what we're able to do by doing this is get volume estimates of the amount of biomass that's been generated in these stromatolites and compare that to how long they've been growing. And that gives us some idea of the bioproductivity of these things in the extreme environments. So the last thing I'll do really quick, because it is definitely data hot off the press and in progress, is I really enjoy doing the same thing as I did in that last slide in Puerto Rico, but collecting time-lapse versions of that, meaning go collect data, something happens, go collect data again. So subtract the two and look for motion. So for instance, the way in which this can work, here's an example of just a gravel pit in Grand Junction. And we just took a bit of shovels and scraped those off, little shovelfuls off of our gravel. And we took before and after data. And when you subtract those two, you get an image that looks like this. And what do we see? Well, we actually scraped a little bit of gravel here and we made a little pile here. And we scraped a little gravel here and made a pile here. Scraped a little gravel here and made a pile here. And just so you know, the scale here is centimeters. So we're actually using these data to look at centimeter scale movement. And so one of the main ones that came up that I've used this for is not only snow surveys. So this is actually a map that I did in between April and 1st and 10th, 2022. When there's about 3.5 centimeters of snowfall up on Grand Mesa. This is on Grand Mesa. The areas that are white or non-colored means there was not much snow captured, and yet the areas that are in green are where all the snow ended up. So even though when we say things like we got 3.5 centimeters of snow, once you get in complicated environments, here you can see, for instance, the snow filled in the snowmobile tracks, the snow filled in cross-country skiing paths, and then, of course, the snow got packed behind the trees in here like snow fences. And so one of the reasons I'm interested in this is when we think about groundwater recharge and snow melt into a water resource system, we have to understand how unequally distributed these materials can be. My last two examples here are to show the West Salt Creek landslide. Many of you will be familiar of that. It went off the north side of Grand Mesa. It was pretty substantial landslide. It was several miles long, and unfortunately, there were some fatalities. Here's the head wall of that landslide right in here. This is the block that pulled away from that slope and left this in here. Well, right after this happened, the U.S. Geological Survey flew some LiDAR in here to get a high-resolution image. Well, I went back in 2022, so 8 years after the fact, and reacquired data here to see how that landslide may have been moving slowly, but how that may have been moving over the last decade. So the first thing you see is the big cut stream where the sag pond behind it is cutting down through the head of the landslide. And then you also see very familiar patterns that we saw in that gravel where you have losing material and gaining material. So the good news is this whole head wall is not breaking simultaneously, and we don't expect a reactivation of this landslide. In fact, it seems to be degrading relatively stable, which is fortunate in here, okay? I really want to quit, so I'll just stop really quick without talking very much about it. But one of the things I did is went out right after the Pine Gulch fire where we could get in and get access. And then I've been collecting data generally every 2 months to every 3 months. And one of the things that I'm doing out at that site where we had big burn areas over regions of very high topography is collected drone data, and then went back and reacquired the drone data. You can see here left to right. And then I subtract those two drone data sets from each other, and I can look at where we have a loss of material at the high steep parts of the slope, and that material moving downslope and ultimately getting into stream drainages. So again, we're just getting into this now. We did this May and then October, and we're going to go back again right after the snow melt in the spring and look at these processes. So I appreciate your time. I apologize here for going a few minutes over, and hopefully you care about geophysics, or maybe it's just me. So with that, I thank you for your time and appreciate the opportunity to talk to you all.
You came with a lot, man. That was such a good introduction to the techniques that you've been using. I found that fascinating.
Okay.
We have time for questions. We still have a lot of participants here in the call. So if
I'm
anybody...
happy to stay if, yeah, I'm
great.
happy to go, yeah.
So if you do have questions, feel free to put them in the chat box or the Q&A. If you have to go, I understand. You will be getting a recording of this video, so you can always check back in tomorrow for the questions.
And also, sorry
Yeah.
to interrupt, also people know where I live now. So you can just Google me at Colorado Mesa. If you got some questions you weren't able to ask or anything else, I'm happy to, field emails and talk to folks.
That's great. Well, the one question we have right now is actually not about the Grand Valley, but a pretty significant topic to get into. Kara is wondering if you have been following the train wreck in East Palestine, Ohio, and what are your thoughts on the remediation plans to incinerate 700 tons of topsoil and other risks to the soil and groundwater?
Yeah. It is a horrible situation for numerous reasons. It is a horrible situation from the perspective of figuring out what to do because there are so many unknowns. And so what I will first say is I don't have very much intimate knowledge of any of the sort of geotechnical details of that site and the contamination in itself. I can tell you that certainly the thought process, again, remember earlier I talked about good intentions often go awry. I think the thought process behind burning was the last thing we want is this material getting into the groundwater, because if you got anything out of what I talked about on the environmental side, it's that once it's off the surface and in the ground, it is incredibly hard to track down and keep track of. And so I presumed, as I was following the story, that what happened is without enough forethought, people said, we want to burn this off now, because if it goes into the ground, we're going to be dealing with this for 200 years or more, right? I mean, I talk to people in Oak Ridge and they say, yeah, I mean, we're never going to get all the uranium contamination out of Oak Ridge. So right now they're just trying to contain it in the Oak Ridge facility. So I think the concern there, and again, don't take away that I thought setting that all up in flames was a great idea, but I do want you to recognize that I think was the idea. And I don't think it was, let's burn it so our problem is gone. I think it was, we think this will get worse and in effect a larger area and more people if we don't do something now. So what this certainly comes down to is, and again, I'm no expert on this, but as we think about rail systems and transportation of hazardous waste, certainly this is an area where somebody ought to have had a plan in place for what happens when this happens. And it shouldn't have been, the sky is falling, let's set it on fire kind of thing. Fortunately, there are some things that could still be done without burning it. There are ways now to drill boreholes in the ground if we catch it soon enough, and do pumping to change the gradient of the groundwater and keep the contaminant from flowing outward. But of course, one of the things I can tell you, knowing a little bit about that region, is it is generally underlined with highly fractured limestones and sandstones. And so it's really a worst case scenario. And, without trying to be sort of too glib about it, it really is a case where what you wanted to have happen was not the spill in the first place. Because once the spill happens in that geological environment, there are really no good answers. And if there's anybody out there who has family or things like that. I apologize if that sounds sort of doom and gloom, but my experience with other sites is that's definitely the reality to these complicated geologic situations. And then, of course, compounding the problem is how it's kind of, crudely, but it fits with sort of, nuclear reactor accidents, where the other bad thing you want to do is who's going to decide who's going to go to that site. Who's going to go walk around in that stuff and plant geophones or do ground penetrating radar or something to try and figure out what's down there? And that's another horrible decision that has to be made. So it's a great question, and I unfortunately feel like there's no good answers, and it's going to be one of those that we're going to be wrestling with for a while.
Well, definitely, and I hope that, I don't know if you found in your work, but by studying these problems, whether some of the research that you're finding ends up leading to certain policy decisions, or, learning from our mistakes and finding ways to prevent issues in the future.
Yeah, I agree. And that is why I do what I do. And what I mean by that is, I could be doing research working for the U.S. Geological Survey. I could be employed by Oak Ridge National Lab doing research. But what I like to do is I like to do sort of really high risk exploratory work, which, can get you fired from an environmental consulting firm because they want things that work, well, and you're not expending people's money for no reason. But the hope is in doing that is occasionally you get these things that do work well, and hopefully will eventually get translated into more widespread usage and help with these problems.
Yeah. Well, let's see. We have, to end on a positive note, do you have any examples of good news you've been involved in Colorado?
Yeah, so I think probably one of the interesting things I found is, it's a bit of a long story, but I've been coming out here to the Grand Valley for 25 years, but during that time, it was generally only during the summer, so I only see one season and all that kind of stuff. And other than that, I've only been out here since 2019. So, and then COVID. So the first thing I'll say is, not as much as I'd like to do all these awesome things. I will probably point out a couple of things that are in the works, and some of those that in a lot of ways are good news, because I think they're going to relate to closure for people. Is I've done some work with various archaeologists on finding unidentified grave sites. So to me, that's a good news thing for the closure side of things, not the grave site of things. And I apologize for laughing about that. You wanted to end on a positive note, but what I do see happening is that is one area that I have done a bunch of work before. I was pretty fortunate to do some work just outside of Gettysburg National Park, and there was some folks had found some documentation of a potential Confederate soldier mass grave, mainly mass because it was during the battle, and this farmhouse was the hospital, and they just buried people outside, and it hadn't really been known about for 100 years. And somebody found an old document. We went out and did some geophysics, and we were actually able to identify several of these features, which once they were carefully evaluated, they were able to find that there were indeed some bodies there. There was attempts at some identification, and now that's set aside as sort of a much more sort of permanently honored position for these folks. So that's one thing that I've been doing some around here, both sort of modern and ancient. We've been looking at some old sites too. So that to me is particularly interesting, and although it's sensitive and one must do those kinds of things with great care, I found that most of the important people who are involved in that are quite grateful to find information either about relatives or ancestors or those kinds of things. So yeah, I guess that's where I'd go for starters.
Well, that's great. I think we're going to call it here.
Yeah.
So thank you so much for all of your time and sharing all of your extensive knowledge and research with us.
Yeah.
This lecture, yes, like I've said a couple times, is going to be on YouTube. I think it's great to have this connection now, and I hope we can find more ways to plug you in with some of our CCA programming, because this has just been fascinating. We're getting some thank yous, and that was awesome in the chat right now. So again, Greg, thank you for your time. Really appreciate it. And everyone enjoy your evening.
Okay. Take care. Thanks, Anne. Thanks for everything.
Yeah.